These days, medical physics is not that popular. Partly, the examiner has exhausted the question already lah. PET scan is the only one new one lah. So sometimes some years they may only like in 2002 only the March paper, February March paper got a PET scan. Okay, let's choose some partial question. Right, I call exercise 24.3. Positron emission tomography, PET scanning. Make use of tracer containing radioactive material that decays by positron emission. State what is meant by a tracer. Yep. This is taken from specimen 22. Specimen 2022 lah, where they introduce this topic, so they have to give you a specimen paper lor. Can?
Yeah, it's a radioactive isotope.
Not sufficient. A substance produced introduced into the body, absorbed by the tissue being studied. Okay, it may not be radioactive, but because they didn't ask you what is radioactive tracer, they ask you what is a tracer. A substance
Oh, okay.
introduced into a body, absorbed by a tissue being studied. State the name of the particles that are emitted from the body and detected by detectors during PET scanning. Yeah,
Mm, positron.
gamma photon is the positron that's emitted, but they interact with the electron to produce gamma ray photon. So what you are detected by the PET scanner is gamma photon, not positron.
Okay.
Explain how particles in A part 2 are created from positron. Yep. Positron emitted interact with electron in tissue. Positron is an antiparticle of an electron. Pair annihilation between the two. Matter turns into energy. Okay. The positron and electron annihilate, producing energy. Positron can be artificially created by a process in laboratory. That is the reverse of the process in B. The process creates both positron and an electron moving at the same speed in opposite direction, such as why two of the particles in A part 2 are needed to create one positron. Yep,
What are the particles?
you have two gamma rays meeting together to produce a positron. Why you need two? Why you need two gamma rays? Why two? Suggest why two of the particles are needed to create one positron. Right? The particles are the two gamma rays. Why you need two? Why not one?
Conservation of momentum.
But not sufficient explanation. Same mass, right? Both gamma ray have the same mass. Therefore, combined momentum of electron and positron is zero. Photon have momentum, so must be two of them to conserve momentum. Okay, electron meet positron, conserve. There is zero momentum, so two photon required to produce zero momentum also in opposite direction, meeting to annihilate each other. Okay,
Yes.
this one is February, March 22, paper 42. Positron emission tomography, PET scanning, obtain diagnostic information from information used to form an image. PET scanning use a tracer. Explain what is meant by a tracer. Same, no? Right? Substance containing radioactive nuclide that is introduced into the body. Right? Either that or you can write substance containing radioactive nuclide that is absorbed by the tissue being studied. PET scanning involves annihilation. Explain what is meant by annihilation. Yep. What is meant by annihilation? Annihilation.
Particle and antiparticle meet form energy, converting the rest into
Particle
energy.
interacting with each with particle interacting with its antiparticle so that the mass is converted into energy. The energy appears as photon of gamma rays. Right? Now the particle and interacting with antiparticle. So the mass is converted into energy. Say the name of one particle involved in the annihilation process. Yep,
Photons.
not photon,
The shade.
electron and
Oh,
positron. Calculate the energy released in one annihilation event. This one should be able to do that. We have done that just now, right? Two, because there is mass of electron and mass of positron, right? So we use E equals mc square, and then mass of electron, same as mass of positron, can be obtained from data sheet, and speed of light can be obtained from data sheet. Okay,
yeah.
calculate the wavelength of energy of gamma ray photon release. Right? This one you should be able to calculate. Have you got the answer? This energy produced two gamma rays, each of energy divided by 2, because two gamma rays are produced. The energy we calculate is the energy of the two gamma rays together. So we have to divide by 2 to get energy of one gamma ray. And from that, we use E equals HF. Then replace the F with C over lambda. Put in substitute, find lambda. Can explain step by step. Explain how the gamma photons are used to produce an image.
I don't know how to explain.
Any of these three? Do gamma ray photon travel in opposite direction? 3 marks question. Gamma ray photon detected outside body or by detectors? Gamma ray photon arrive at detector at different times. So that they give different time, give the different location, determine location of production of gamma rays. Right? So they reach the detector at different time, so that is allow us to determine the location of the production of gamma rays. So image of tracer concentration in tissue is produced. So okay, any three of them? 3 mark question. Any comment? Anything not clear?
Okay.
Okay, we have completed medical physics. Let's carry on with our astronomy and cosmology. Okay, we are now in astronomy and cosmology. As I say, we only need another 40-minute session next week. Probably finish Hubler's law. We should finish stellar radius and do some question. So if you've got question to ask on 2022 paper, you can ask. I have done that. The others I haven't done yet. 2003 also, 2023 also. Okay. Sorry, some technical problem. Okay, you can see the picture. If any problem, let me know. Because my quality of sound is very poor. Sometimes cannot hear. Can hear me or not?
Yeah, I can hear you.
Okay, good. Okay, 317. We are now on the first part, 25.1 standard cable candle. We have defined luminosity. Okay. Then we have defined radiant flux intensity. Okay. Then we have defined standard candle. Right? A standard candle is defined as an astronomical object which has a known luminosity due to its characteristic quality processed by that class of object. Right? Some example would be a standard candle, septic, variable stars. Don't worry about the name. type of pulsating star which increases and decreases in brightness over a set time period. Right? Brightness usually means intensity. Radiation is well-defined relationship to luminosity. Type A supernova explosion involving white dwarf. Luminosity at the time of explosion is always the same. Okay, so standard candle approach to distance measurement. Right, there's your standard candle. There's a distance r away from the standard candle. Area A, let's say example there are 16 photons. So when we double the distance, right, that photon there 16 spread out into 4 equal area. Right? This area becomes 4 times, and each area is divided by 4. So the intensity becomes 6, right? I over 4. I initially, so it's 16 divided by 4 is 4, 4 photon. Then if we go 4 times the distance, 4 times the distance becomes 16 square, 16, no? Out to 16 times the same area, right? 16A. So each area there will have only 1 photon, no? Okay, luminosity of the sun we can measure is 3.839 times 10 to the power 26 watt. Distance we can also measure at a distance of 1 atomic unit, 1 astronomical unit. Don't worry about astronomical unit lah. They will give you 1.496 times 10 to the power 11 meter. Right? Astronomical unit is basically the distance between the average distance between the sun and the earth lah. What is the radiant flux received by absorbing atmosphere of the earth? Right? We know the distance, we know the luminosity, so we can calculate the radiant flux intensity using this formula. Right? Put in the value L, that's your L, 4 pi r square, that's your distance. Okay, so that is what we measure on Earth, 1365 watt per meter square. Anything not clear? Anything you want to ask? Yep. Okay. Average annual solar radiation arriving at the top of the Earth's atmosphere is roughly 13161. Right? Roughly where we get our calculation. A star has a luminosity that is known to be 4.8 and 10 to the power 29 watt. A scientist observed the star, finds that the radiant flux intensity of the light received on Earth from the star is 2.6 nanowatt per meter square. Determine the distance of the star from the Earth. Okay, you should be able to play with the formula. L is given, F is given, so you can use the same formula as we used previously to calculate R. What is your value for R? R is the distance. Yep, that formula, use that formula. Then subtract your R, put in your value, right? That's your L. Convert to the SI unit, that's your F. Can get 3.83 times 10 to the power 18 meter.
Okay.
Okay, good. These are some of the things you are going to study later on, right? Just to whet your appetite. Using standard candle as a distance indicator, right? Just like what we have done this question. If we know luminosity, then this one we can measure on Earth. Then we can calculate our distance. This standard candle method can measure distance within a certain range. Collaborating the data and measurement for each method allow astronomers to build up a larger picture of the scale of the universe. This is known as cosmic distance ladder. Right? That's what it means. The sun and the earth, we use radar ranging. Then for stars, nearby stars, we can use parallax method. We don't need to know all this. This is just to whet your appetite in case you are interested. Milky Way, apparent brightness, surface temperature. And then this one is what we use. Luminosity and period. We can measure the period on Earth. Then we can, if the period is there, then the luminosity is known. Then we can measure the F. Right? The other one is measure of distance is using Hubble's law, which is a distant object. Okay, the others are for your info only, just to tell you what what we call cosmic distance ladder. Different method and limitation. So we build up a picture from different method of measuring the distance. Right? These are different standard candle, just for info only, don't bother about that. Using standard candle as a distance indicator, you just use this formula. Radian flux intensity. Measuring astronomical distance accurately is an extremely difficult task. A direct distance measurement is only possible if the object is close enough to Earth. Right? That's direct method, the Sun and the Earth. For more distant object, indirect method must be used. This is where standard candle come in usefulness. If the luminosity of the source is known, L, then the distance can be estimated based on how bright it appears on Earth. We can measure this one on Earth. Radiant flux intensity, or what you call brightness. Astronomers measure the radiant flux intensity of the electromagnetic radiation arriving on Earth. Since the luminosity is known as the object is a standard candle, the distance can be calculated using the inverse square law. Using this formula, that's what it means. There are a few different methods, but one of the most common is the standard candle method. This rely on the fact that if we know how bright, luminosity, how bright an object is in space, really is intrinsic brightness, then we can estimate the distance from how bright it appears on Earth. It's apparent brightness, right? We can measure F from Earth. L rely on the natural brightness or intrinsic brightness. Then we can calculate our R. Okay, there's the graph that we can calculate. We can draw for Cepheid stars. Cepheid variable is a type of standard candle. Right? You can measure the period and the luminosity. Cepheid variable are type of star that have a consistent relationship with their intrinsic brightness and how fast they pulsate. Right? This is the period of pulsate. So you can watch one, and if it pulsate at x speed, right? X speed, from the speed we can convert to period, and then from period you can calculate the luminosity, y, brightness. Sorry, there's some technical problem. Okay, that's the graph that we can obtain from the Earth for luminosity versus period. So if we know the period x, then we can determine the luminosity from the graph. Right? This one is for nearby galaxy of 7 light years. 10 to the power 7 light years. Light years is distant. Measuring intrinsic brightness of Cepheid variable or other kinds of standard candles such as supernova allow astronomers to calculate the distance to the standard candle home galaxy. Okay, so these are the things that we have learned for standard candle. Luminosity, these are terms you need to remember, is the total power. Radian flux intensity, know the definition. Standard candle, know the definition. Right? Astronomy and cosmology is a new topic. So examiner tends to have more questions to ask. So we can expect every year this one will come out. Okay, we go to stellar radius. Right? Stellar radii, that's the syllabus. Right? We call that formula. No need to know the constant. Right? We got 10 more minutes. Stephen Boltzmann's law. Using Wien's law and Stephen Boltzmann to estimate the radii of the star. Okay, first thing we need to know is black body. A black body is an object which absorbs all radiation that falls on it. Right? It doesn't reflect. It's a good emitter. It emits all radiation, all wavelength. Does not reflect or transmit any radiation. Right? Memorize what? Black body is a theoretical object. However, stars are the best approximation. Right? That's what scientists think. Radiation emitted from black body has a characteristic spectrum that is determined by temperature alone. Right? That's a spectrum. Power density. This is a wavelength. Change in visible color of stars of different temperature can be traced out as a chromaticity diagram. Okay? It's taken from hyperphysics. Stars approximate black body radiators, and their visible color depends upon the temperature of the radiator. The curve show blue star if it has a temperature of 7,000 Kelvin. This one is 5,270. This white star, right? White in color will appear to us white. And then this one is 4,000 Kelvin. Right? The maximum is towards the red star, red wavelength. The white star is adjusted to 25270 Kelvin so that the peak of its black body curve is at a peak wavelength of 550 nanometer. Right? We are not interested in the peak wavelength. peak power at a particular wavelength. For the wavelength at the peak, the temperature can be deduced from Wien's law. Right? Wien's law summarizes the maximum temperature and the wavelength. Right? That's what this graph is showing you. Intensity wavelength graph show how the thermodynamic temperature links to the peak of the wavelength by 4 different stars. Wien's displacement law states that a black body radiation curve for different temperature, the wavelength of maximum intensity is inversely proportional to the absolute temperature. Memorize this law. We're very interested in wavelength at maximum intensity. Right? That formula, memorize it. Lmax is the maximum wavelength emitted by the star at peak intensity. T is the absolute thermodynamic temperature at the surface of the star. Wien's displacement law relates the observed wavelength of light from the star to the surface temperature. So by looking at the star and the color of the star, we can use Wien's displacement law to estimate the temperature of the surface, thermodynamic temperature of the surface. Okay, there is a table. Yellow is between 5,000 and 6,000. Red is less than 3,500 Kelvin. The full equation, that one, if they want you to calculate, they will give you this value. They give you this value. This equation tells us that the higher the temperature of the body, the shorter the wavelength at the peak intensity. So hotter stars tend to be white or blue, and cooler stars tend to be red or yellow. The greater the intensity of the radiation at each wavelength. Right? So the lower the wavelength, the greater will be the intensity. You can see from the graph there. Okay. Lower wavelength, greater intensity, and higher the temperature. Any comments so far? Or anything that is not clear?
Okay.
If you are study astronomy, then they will introduce you lah. The constellation diagram I can picture as a man lah. Orange constellation, cooler stars such as Betelgeuse, which is here, while hotter stars such as Rigel, which is here, appear blue or white or blue. Okay, do a calculation. Give you a chance to do that. The spectrum of star Rigel in constellation Orion peak at wavelength of 263 nanometer, or the spectrum of star Betelgeuse peak at a wavelength of 828 nanometer. Which of the two stars is cooler? Right? If they want to calculate, they have to ask you to calculate lah. But this one you can look at the wavelength. Cooler one, lower temperature, lower temperature over 828. But I think this one they want you to calculate lah. Right? Using this formula to calculate, if they want you to calculate, right? Temperature of Rigel. Okay, that one change it to SI unit. Okay, Betelgeuse temperature there, right? That's a wavelength. So we can see this is cooler. Okay or not?
Yeah.
If you don't require to calculate, you can use this formula lor. This is a constant lor. Lower wavelength, higher wavelength, lower temperature. Okay, Stephen Boltzmann's law. Right, you got 2 more minutes there. Anytime we cut off. Star luminosity depends on 2 factors: its surface temperature, its radius. The relationship between these is known as Stephen Boltzmann's law, which states total energy emitted by a black body per unit area per second is proportional to the fourth power of absolute temperature of the body. Right? Relationship can be written as an equation. No? Right? Luminosity is where L is luminosity of the star, luminosity of the star, R is the radius of the star, not distance, radius of the star. This constant, sigma, is Stephen Boltzmann's constant. Right? The value is given in your data sheet. This is the surface temperature of the star. Right? Don't careful when you use this formula. Right? This R is not distance. This star is radius of the star. But anyway, this is given, so you don't have to worry about summarizing this one. It's just to caution you. You can write it this way, but careful that this is not distant radius of the star. Any comment?
No.
Okay, so in summarize, that is a formula that we have learned. You can try the past year paper that I've given you, and then use the note to help you where I've learned teaches you. So I will need only 40 minutes on Tuesday. So any question you
Okay.
ask? If not, I will stop here.
All right.
Okay, if not, I will stop here. You can go. Thank you.
All right. Thank you.